thank you, Culver, and thank you to my 100% of audience who are attending and the rest of you who are online. Hopefully it's not such a terrible experience. This is the first time I've given a public lecture to a hall completely full with 10 people. But I have been absolutely delighted to take part in the group's GRA program this semester, and it's sad what's happening to our world and our country, but I hope that there'll be some good things coming out of the program. I'd especially like to acknowledge and thank Dr. Ewan Kirk for his generosity and his enthusiasm and his strong support of mathematical sciences at the Newton Institute and thereby throughout the country and much further. And I'm honoured to be a Kirk Fellow, and I hope that I can pretend that I'm talking to lots and lots of people. It's supposed to be a public lecture, so I really did choose something which I hope would be very accessible. I really am going to talk about shuffling cards. I will be focusing on perfect shuffles, and I'm going to talk about where these questions came from. In particular, some early work of Percy Diaconis, Ron Graham and Bill Kantor. I'll say quite a lot about some of their work, and then some other work, and then some new joint work with two young colleagues, Carmen Amarra from the University of the Philippines and Luke Morgan, now at Primorska University in Slovenia. They were both at the University of Western Australia for a year when we were doing this work. So, let's go. I wonder if I can make this work the right way, correct. Good. So, a perfect shuffle. We have a deck of cards which we assume has got an even number of cards in it. And to do a perfect shuffle, we cut the deck into two equal-sized piles. And if I were a magician, like a colleague of mine, Percy Diaconis, I would be able to do something like that picture shows, because we cut it in two and then we perfectly interleave the cards. I have only once seen someone do this, and that was Percy, and he did it once when we were both at a Mount Baldy conference in Harvey Mudd University in California. It was a fantastic lecture he gave, and that was a real public lecture with lots of people. Well, from what I said, we cut the deck into two piles, and we perfectly interleave the cards. What would we do? Well, in fact, there's kind of two ways that you proceed. So we had maybe the top card of the original top card. We might take it up first, and then the next, and the next, and the next, and so on. And we would thereby be changing the ordering of the cards. So if, in fact, we just had 12 cards, which are labelled 0 to 11, this is called an out shuffle, where the outside card stays on the outside. So we would pick the 0 card up first, and then maybe it's easier to see if I wrote down what's happening. We would have the cards like this, and here would be 0, 1, 2, 3, 4, 5, and 6. So we would pick them up at 0, 6, 1, 7, 2, 8, and that would be the resulting ordering at the end of an out shuffle. But if we instead, that didn't work, did it? If instead we did it the other way round, so instead of taking the original top card first, if we started with the other pile, we'd go 6, 0, 7, 1, 8, 2, etc. And we would get quite a different reordering the cards after the in shuffle. So you can do an in shuffle, you can do an out shuffle, you can do either of them any number of times, one after the other, and there's many questions that might be asked by card players and even by mathematicians. Like, could you get the top card into any given position? Or how many different reorderings of the cards can you get by repeating these in and out shuffles? Or maybe how to alternate the shuffles in and how many to do in order to get a somewhat random reordering of the cards. Or maybe a mathematician might say, well, exactly how many different orderings could you get? Does it depend on n? How does it depend on n? What sort of maths is going on? So to give us a little bit of language to talk about, we interpret the in and the out shuffles as permutations of the cards. And this one I always get wrong. So I think I've got it right, having assiduously gone through correcting all my slides. So what is going on? We start out with this ordering, and after the out shuffle, we get that one. So notice that the 0 card stays where it is, and the last card stays where it is, 2 fixed points. What happens to card labelled 1? Well, it's picked up 0, 1, 2 in the tooth, where what used to be the tooth place. So 1 goes to 2. And then card 2 gets picked up with what was the 4th place. And 4 gets picked up with what was the 8th place. And so we get a reordering like this, and you just get, at least when I've got 12 cards, you get 2 fixed points and a cycle of length 10. Let's try it with the in shuffle. It, of course, looks different. Now the 0 card is the second one that we picked up, so it's in position number 1. And then the 1 is in what used to be position 3, and then 7. And we continue, and we see that we get a 12 cycle. Now, I'm not saying this is what happens for every size pack of cards, but at least the in and the out shuffle look rather different. And we can define the shuffle group as the set of all the permutations obtained by performing any sequence of ins and out shuffles any number of times in any order. And that will form a subgroup of permutations of the group of all permutations, the symmetric group, on the 2n cards, which I'm going to label 0 up to 2n minus 1. So we've got this shuffle group. How big is it? What about its structure? Does it depend on n in its structural way? And if so, how? Well, here's when I would like to start talking about Percy and Ron and Bill's work. They published a gorgeous paper in 1983. Maybe I'll just start calling this DGK because I'll be talking about it quite a lot. The paper's lovely. I recommend it to anyone that would like to just read a little bit more about this. Of course, they explain that they're not the first people, they're not the first mathematicians, they're not the first card players to look into the mathematics underpinning shuffling. And in section 3 of the paper, they give an overview of earlier work, and some of that overview goes right back to things published in the 1800s, yeah, 1900s, Collie, 1900s, no, 1800s, yes, 1800s. As far as mathematicians go, they highlighted, on the one hand, work of Alex Elmsley, 1957, who realized the importance of the order of 2 modulo 2n minus 1, by which I mean the number of times you have to multiply 2 by itself until you get a remainder 1 when you divide through by 2n minus 1. And I think we'll see that a little bit later, or something like it. But in particular, a few years later, a paper published by Gollum, 1961, looked at what was happening if instead of 2n cards, you had an odd number, 2n minus 1, and you tried to do more or less the same thing, because someone looking on couldn't really tell whether you had cut the deck into n minus 1 over 2 and n plus 1 on 2, or you really had an equal number. And he showed that the shuffle group, the number of different permutations of the cards, was, it had order 2n minus 1 times this O of 2 mod 2n minus 1. You will very soon see that this is a very small number. Compared with what happens when you've got an even number of cards, this is really tiny. Another part of the paper discusses applications of these card shuffling theories to parallel processing, where you imagine two processes which are going to get sort of linked up in lots of different linkages, and maybe thinking of the shuffles as some of the permutations of the I forgot what you call it, of the endpoints of these parallel processing nodes. But for a mathematician, for a group theorist in particular, they worked out the shuffled groups. And so I show you a slide which you're not supposed to look at in detail, but I'll talk about a few features of what's there. Now, one of the features is that there's two generators. One of them is the out shuffle O, and the other is that you could review what you might mean by an in shuffle, because shuffles are quite complicated objects. So you could say, being a mathematician, what is an in shuffle? Well, I cut the pack into two, and I'm going to shuffle them and interleave them, but I'm going to start with the wrong pile. So instead of doing that, I could swap them and then do the original one, so that I only have to think of one complicated move, the out shuffle. But what is that, what do? We cut them and we swap them. How is that supposed to be thought of as a permutation of the cards in some order? Well, just imagine that you did that. So you cut the pile of cards, you swap them, and then you reorder them by just swapping the top half to the bottom half, yeah? And so that's a much simpler permutation of the cards. So what we would have done was we put them in this way, and then we would have stuck this spot on top of the others. And so you go 6, 7, 8, 9, 10, 11, 0, 1. So it's that kind of reordering, and work out what permutation that was. Okay, that's one thing. So you could think of the shuffle group as being generated by our out shuffle and our pile swapping permutation. Now, next thing is, don't read this too much, but it looks like there are various families which depend on the residue, the remainder, when you divide n by 4. There's something happening a bit different when n is the power of 2, and there's a couple of small exceptions. And what's happening here is kind of complicated, but we're not looking at it too much, because I just wanted to show you a picture. Because what we're really thinking of here is the bits and pieces that make up the shuffle group, which mathematicians would, this is where I'm terribly embarrassed talking to the 10 of you, would think of as the building blocks of the group. Now, this image was something which was chosen to be shown in a 2-minute video of the announcement of the Prime Minister's Prize for Science in October last year. The media company, Porter Novelli, and the company that produced the video, as well as people from the Prime Minister's Prizes for Science, really wanted something that they could say was an image of what group theorists did, what my research was all about. And after 5 or 6 goes at doing this, they had me explaining that the way that you compose a group is that you split a group into 2 parts, and each of those parts is a smaller group. And it's a bit like the branches of a tree. And each of the smaller parts you might split again into 2 even smaller parts. Nothing like words like normal, subgroup, and quotient. None of that. And you keep splitting and splitting until you can't split anymore, and at that point you're at the leaves of the tree. And the leaves of the tree are like the building blocks of the group, and you can tell quite a lot about the group, something about the structure of those leaves. You can tell how big the group is by looking at all the leaves. You can multiply them all together and the sizes, and you get the size of the group, for example. So what were these leaves of the tree in the shuffle group that Percy and Ron and Bill had discovered? Well, they found something quite extraordinary, which I think is very, very beautiful. They understood and discovered and presented that there's a thing called central symmetry. Maybe they didn't do it, maybe lots of people had known about it, I don't know. But it's very beautiful. There's a central symmetry that's preserved by an in-shuffle and an out-shuffle. And here I've just written down the starting order, and then what happens after the out-shuffle, what happens after the in-shuffle. But I'd like you to nominate any card you like. And if you don't, I'll do the red ones, but 9, okay, 9. So where is 9? It is 1, 2, it's the third in from the left, the right, yeah, the right. And it's going to be sort of paired with the third in from the left, which is 2. And after the out shuffle, where is 9 and 2? Well, again, 9 is 1, 2, 3, 4, 5 from the right, and 2 is 1, 2, 3, 4, 5 from the left. And after the in shuffle, here we are, 6 from the right and 6 from the left. And if you'd done it with 8 and 3, you could see they might have crossed over a bit. But the pairs, the symmetrical pairs as you move in from the outside, always get moved together by the in shuffle, by the out shuffle. And the typical shuffle group on 2 N cards involves a swapping, usually independently, of these N pairs of cards, so that the typical largest group is going to have, in fact, N copies of a cyclic group of order 2, which just swaps the centrally symmetric pairs. And it also involves, typically, the symmetric group of all permutations on the N pairs. And so the typically largest group, which actually happens for one of the residue classes, mod 4, has exactly that order. It has N copies of the group of order 2, and it has the symmetric group of degree N, which has size N factorial. That is big. Like, remember when you just had an odd number of cards? You essentially got N times log N, and this is like 2 to the N times E to the N, or more. Sometimes you would miss out on one of these, and sometimes you would, instead of the symmetric group, get the alternating group. It just depended on a bit of congruence as mod 4. And that's mainly what was happening for almost all the values of N. At the top of that table, we noticed that there was a special case when N was a power of 2, and in that case you still got all of the swaps of the centrally symmetric pairs, N of those, but on top of here you just got a cyclic group of order f plus 1 where N is 2 to the f, so it's essentially a 2 to the N log N. You've traded an N factorial in for log N. It is much, much smaller. So that's what they discovered, this very special case. And there were 2 small cases, which makes the group theorist's eyes light up. N is 6 and N is 12. So you've got either 2 times 6, 12, or 24 cards altogether. And instead of getting the symmetric group S6 on top, you just had a PGL25. It's sort of 6 times smaller, yeah? And then instead of having a symmetric group S12, you've got the Mathieu group M12 occurring. Quite surprising, quite lovely. So group theory says why and what's happening. And here is our logo for the whole program. So this is the periodic table of the finite simple groups. These are the building blocks, the leaves of that composition tree I showed you. And we might say, well, where out of all of these simple groups, which are the ones which are occurring in the shuffle groups? So this is a beautiful diagram made by Ivan Andrus for his father on Father's Day to help explain how these building blocks were really the objects from which all simple groups arose, rather the same way as the atoms in chemistry describe all compounds. So most of the simple groups are in the central portion, and they're the groups of Lie type, and there's only one, and I'm faking it a little bit here. The smallest A1 group is going to take the role of my PSL25. We get all the cyclic groups down here, but only the top one occurs, the cyclic group of order 2. And then right over here, there's an extra column which is for the alternating groups. We get all of them arising as the big major part of the symmetric group Sn. So all of them come through this one, and down the bottom are the 26 sporadic simple groups, and exactly one of them arises in the shuffle groups. So the shuffle groups are actually quite interesting, that they're producing, some simple groups of each type in a sense. So where do we go from there? That was more or less what Percy and Ron and Bill had done. And in fact, Percy had suggested to some American colleagues that they might study the many-handed shuffler. So instead of cutting the pile into 2 piles, pack of cards into 2 piles, you might have k times n cards and cut the pack into k piles, each of size n, and perfectly interleave them. So here's my top card, top pile. I'll do 0, 1, 2, etc. And that would be my out shuffle. And I could do that. That's fine. I could do it. Don't know what sort of reordering I'm getting. But that's my out shuffle, picking up the top card from each of the piles in turn. Maybe I really should draw another picture here, because I'll be referring to it a bit, and I'm for sure going to get messed up. So if I had 12 cards again, and I'm going to put them into 3 piles of size 4, it would look like this. And then I pick them up in order, 0, 4, 8, 1, 5, 9, etc. And I get the output ordering, and I ask what permutations of the cards has happened. Well, of course, again, the first and the last remain the first and the last, and this time I find the 1 in the position of 3, and I guess I want to know what happens to 3. Well, 3 is in the position 9, and we keep going, and we find that there's a product of 2 cycles of length 5 for this out shuffle, and that's fine. But now, what should we mean by the in shuffle? We're not going to get far if we've only got one sort of shuffle that we're going to do. Remember that we said for the case of 2 piles, we could think of the in shuffle as swapping them and then doing the out shuffle. So for this, we could maybe decide that since we're not sure what the in shuffle should be, maybe we would give ourselves free choice of what kinds of permutations of the piles of cards we will allow, and then see what happens. So sort of what I'm thinking of, we might choose an arbitrary subgroup of permutations of the piles of cards and follow that up by an out shuffle, and that will generate our shuffle group. So now there's even more questions like, does it matter what you choose for capital P? What's it going to look like? So again, we're not the first, because we just looked at this last year. But Steve Medvedoff and Kent Morrison have published another beautiful paper in Math Magazine 1987 about this question. And I think that Percy was in touch with Kent and suggested that he work on this stuff. I heard about this problem from John Cannon, who's the author of the magma system, who gave me some details about some early computational information which I think he must have done with Kent when he was visiting him in America. And I have this funny bit of paper that I've had in my files since about 1986 or so, not really understanding it, and maybe I'll sort of understand it a little bit later. I understand parts of it, I still don't understand all of it, and it's just been there, sitting there, and I thought when I had Carmen and Luke around last year, I thought, why don't we get this out and see what's going on? So there must be some reason for me to say this. So what had we found in Medvedoff and Morrison's work? So I'm going to call them MM. They really focused on the case where you were allowed any permutation of the piles of cards. So their capital P was the symmetric group on the K piles. They found in the paper that if n was a power of k, then again something especially small seemed to be happening, and it was rather like the DGK information. I guess this would be a generalisation from 2 up to k. Their shuffle group was like the symmetric group on k instead of the cyclic group of order 2, which is a symmetric group on 2 points, extended by something tiny. So k to the f becomes a CF. So they found this, and that's really nicely written up in their paper. A rather nice little lemma was to work out when you translate the outshuffle itself and what is happening with all of these permutations of the piles of cards, whether they're actually even or odd permutations of the set of Kn cards. And it depends on congruences mod n and k. Sometimes your shuffle group consists of all even permutations, so it's contained in the alternating group. Other times you have some odd permutations. So that's done there. And then they did a whole lot of computation in the case where you had 3 piles, like here, or 4 piles with different values of the size of the pile. And something extraordinary seemed to happen. So instead of getting this nice central symmetry and the C2s and the SymKs coming in, instead of that, they seem to come up with very often getting the giants, the symmetric group on the Kn cards or the alternating group on Kn cards. And they made this conjecture in their paper back in '87 that said, if you're not in this power case where the number of cards is a power of k, the number of piles, if you're not in that case, or if you're not pseudo in that case, so you've got 4 piles and maybe you've got an odd power of 2 as the size of a pile. If you're not in that case, then they conjectured that the shuffle group should actually be a giant. You should get almost every permutation generated, or possibly every even permutation. So that's where we started on our work. So we decided, after looking at this, that we might focus on that conjecture and see what we could do. So most of our work was focused on trying to say something about that conjecture. And so I thought I would tell you, spill all the beans and just tell you where we got to. In some ways we got a long way, in other ways the thing is totally untouched. So what have we found? So definitely we were looking at allowing a totally arbitrary permutation subgroup of the piles of cards. Okay? So we were able to show that this power case was also special no matter what permutation group P you put in. We decided that we would look at certain properties of the permutations of the piles of cards and see whether there were somehow some similar properties of the shuffle group. I'll tell you a bit more about that later. We were able, through doing all of this, to confirm the MM conjecture, that usually that you get a giant. in 3 cases. And the first case is quite a big case, but perhaps the less interesting case, when k is bigger than n. It was really hard work, but we did it. We also confirmed the conjecture when k is a power of 2, at least 4, because of course you wouldn't want k equals 2, because then you've got this central symmetry and you're not getting the, well, we knew what was happening then. And also when k and n are both powers of some smaller number L. And we got quite a lot of insights, and I'd like to tell you a bit about what we've discovered. So, first thing we asked was, I've got, say, k piles of cards. If I'm going to allow myself a transitive group permuting the piles of cards, so transitive means I can get from any pile to any other pile using one of my permutations in P. Question, does that mean that the shuffle group is transitive on the set of cards? That is, can I take any card and position it anywhere I like? And our answer is going to be yes. And so I'd like to just talk through how on earth we would do this and what kind of mathematics might be hiding here. So I already explained to you how you would, in the case of 2 piles, take a permutation of the piles and interpret it as a permutation of the set of cards. And so, for example, what am I doing here? The set of cards I'm labeling from 0 up to kn minus 1. The set of piles of cards I'm labeling from 0 up to k minus 1. And so this is pile 0, and that's pile 1, and that's pile 2. And if I wanted to, say, swap the pile 0 and pile 1, then in fact I'm swapping the cards 0 and 4, 1 and 5, 2 and 6 and 3 and 7. Yep. So every permutation of the piles of cards is going to, I can just write down what the permutation of the set of cards is going to correspond to it. And if I'm given enough permutations of the piles of cards that I can get from any pile to any other pile, then just using those permutations, those row of towels, I'll be able to get anywhere in any sort of horizontal layer. I'll be able to take any card in a certain horizontal layer to any other card in the same horizontal layer. And the only extra thing I've got in my shuffle group is the shuffle itself. So what we need to do is to look at the shuffle and see that there is enough happening there so that I could look at any 2 layers and find at least one card in this layer that under the shuffle would get, or under certain sequence of applications of the shuffle would get me to some card in the other layer. And then I would get transitivity. So of course you could just do this bit by bit, but let me show you some sort of mathematics that's happening here. And we'll do it just for this particular case. We've seen that the shuffle itself of these 12 cards fixes 0, fixes 11, and we've got 2 cycles of length 5. But let's just have a look at those cycles of length 5. And as we go through them, 1 goes to 3, which is 3 times 1. Where's 2? 2 goes to 6, which is 3 times 2. 3 goes to 9, which is 3 times 3. And 4 goes to, 1. Well, 3 times 4 would be 12, and if I subtract off 11, I'll get 1. I keep going. 5 goes to, I'd like to do 3 times 5 minus 11. Well, that's 4. That works. This one works. This one works. This one works. And we get down to 8. 8 is going to 2. 8 threes are 24. We'll subtract 2 lots of 11. So in fact, what's happening is that the shuffle is a bit like, we've got to fix the 0, but for every other point, the shuffle is like taking the card label and multiplying it by 3, that is by k in general, and you take the remainder after subtracting off enough of the kn minus 1, the number of cards minus 1. But the reminder's got to be somewhere at least 1 because you don't want to get back to 0. So we've got some kind of nice mathematics going on there, and so of course it's not all that difficult mathematically to show that you can mix up all these horizontal layers and get yourself one orbit under the whole shuffle group. We kept going, but in preparing the talk, it occurred to me that we didn't stop to answer this question over here. So what we've said is if you input a transitive permutation group on the piles of cards, you output a transitive group on the set of all the cards. What happens if you input an intransitive group on the set of piles? What's going on for the shuffle group? In fact, we don't know. We haven't even thought about answering it. I just looked at the case where there's 3 piles, and I tried out all the intransitive ones, and each one of them gave me an intransitive shuffle group. So who knows, out of a very tiny amount of data, what's actually going on there. But we were more interested in Medvedoff and Morrison's conjecture, where they were interested in putting in the full symmetric group as their input group of pile permutations. And we've considered transitive groups. So for group theorists, the next interesting thing to do is to say, well, what if we inputted a primitive group? Input a primitive group P, do you output a primitive group on the set of cards? Is a shuffle group primitive? Well, first off, what is primitive? Means that we're only preserving the trivial partitions on the set of piles of cards, and this is my favorite example of something that's not primitive. So if I take the rotations and reflections of the square there, I get my dihedral group, and this is not primitive because pairs of corners which are opposite are going to get mapped to opposite corners by all of these reflections and rotations, giving me a partition 0, 2 and 1, 3, which is not trivial. Trivial means that you might only have one set in your partition, or all your parts are going to have size 1. So to be primitive, the only invariant partitions are the trivial ones. And we've seen that in the DGK work, if you've just got 2 piles of cards, there's this central symmetry which is preserved. And so the shuffle group there is not primitive, but you're allowed to swap 2 piles of cards with a primitive group of size 2. So it can't just be primitive in, primitive out, because that's not what's happening. So what we thought was, well, there's something special about cyclic groups of size 2. They're not only transitive, they've got something special, they're regular. So that means a regular permutation group is one where for each point pair, transitive would say there's an element of the group P that maps the first to the second. Regular means there's exactly one element in the group that maps the first one to the second one. And a neat fact about the primitive groups is that the only ones which are primitive and regular, well, they occur if the number k is a prime and the group there is a cyclic group of order P. And we recall this is what was happening there. You got something a bit strange. So our next theorem was that if you input a primitive group that is not regular, then you do output a primitive shuffle group. Cool. So in some sense, that's fine. Can't do any better because of the C2 example. But that's a bit weak. So what about the odd primes? I mean, maybe we should try harder. Maybe that was the only counterexample. Well, if k was an odd prime, and if we inputted a regular cyclic primitive group on that number of piles of cards, we could prove that if the n happened to be a power of p, then you in fact did output an imprimitive group. So really, for no primes p, could you simply remove that restriction. On the other hand, Luke was getting very exercised by this. He thought, well, this is really special. I mean, CP is special enough, but then you've got n as a power of p. What if n is not a power of that prime p? So he did a lot of computation. He took all the odd primes of p right up to 13, and for each of those, all of the numbers up to 1,000 which were not powers of p, and discovered that the shuffle group was always one of the giants. Now that's pretty amazing. I mean, Medvedoff and Morrison are conjecturing that if you inputted a whole symmetric group, that you should get a giant, except in these cases. And we're finding computationally that even if you just put in a cyclic group of size p, you get a giant. Computationally, no idea how to prove this. So this is one of our new conjectures, that we think that there's a whole lot more happening that we don't really understand. Okay. I should keep going too slowly. So let's tell you something about what we did manage to prove. So we did, as I said, show that the power case, where the size of the piles n is a power of the number of piles, that we discovered that that's actually quite special for any input group capital P. We get that the shuffle group is a wreath product, the wreath product of P with the cyclic group on top. And so that's a generalisation of both the DGK and the MM results there. That's quite nice. Quite happy with that. But that's just one little part of what's happening. You don't usually have a power of K as the number of your cards. So then we thought, well, transitive in, transitive out, primitive non-regular in, primitive out. What else might we think of preserving? So we thought, well, what about having an affine structure on the piles of cards? So what if we had a finite vector space? So K would have to be a power of some prime P. What if the number of piles is a power of a prime? And what if every element in our input group G is acting as a non-singular linear transformation followed by a translation on the piles of cards? So we've got an affine group coming in. What might you expect to come out as the permutation group? And so we proved that you actually do get an affine structure on the output set of cards whenever you can. So if you're going to get an affine structure on the set of cards, it'd better have the size, a power of P. So it's got to have the same prime P. So if the n actually is the power of P, input an affine group, output an affine group. Yes, that was nice. It would be nice if we could say, and if n wasn't a power of P, then you output a giant. We can't really say that. But in some circumstances, we managed to. So you have to forgive us that we can't do any better than what I'm telling you. In the case where K is bigger than n, and if, for example, you inputted the full affine group, at least a two-transitive one, then we could prove that you output a giant. And in this circumstance with these particular parameters, not a power of P, K bigger than n, something else, it is proving the conjecture for that situation. But this last bit relies on the finite simple group classification. And I'll explain why we would be so brutal as to employ such deep mathematics on card shuffles. I'll come back to that point. So we've done affine, affine in, affine out if it can. It might be that your number of piles of cards is a power of a smaller number. Maybe it's L to the E. And it might be that of your input permutations of the piles of cards, they preserve that Cartesian decomposition. So what that means is all of your the labels of your piles of cards, they're all tuples from a set of size L, and the permutations that you are allowed, they can act as permutations of set of size L independently on each of the entries, and they can permute the entries. So what if you input a permutation group that preserves the product structure? Do you output a shuffle group that preserves a product structure? And the answer again is yes, whenever it can. So what would we mean there? If K is L to the E, as long as the number of cards is a power of L, then we prove that the shuffle group does indeed preserve a product structure. So all of that was kind of sweet. Not that we really understood quite what was happening. It doesn't give us much towards the conjecture yet. So we've looked at transitive groups, we've looked at primitive groups, and I did mention, without really mentioning it, the next one in here is another smaller circle of two transitive groups. It still contains the symmetric and alternating groups, which are our target. And two transitive on K points means that firstly the group is transitive, and secondly the stabilizer of, say, the 0 pile is still transitive on all the rest of the piles 1 up to K minus 1. If you input a 2 transitive group, do you output a 2 transitive group? Well, we actually haven't been able yet to say yes to that properly, and so that's why I've got this thing in a great big red box. So here we started having problems, you know, inputting something, outputting the same property, and we decided that we could make it work if the number of piles was bigger than the size of the pile, bigger than 2. And in that case, if you input a 2 transitive group, then you output a 2 transitive group. And we were thinking, wouldn't it be nice to just leave it at that? Because that's quite elementary stuff that we've done. You know, nice working with cards and permutations. But we asked ourselves, well, all of the finite 2 transitive groups are known explicitly using the finite simple group classification. They're all either affine or they're almost simple. We've already had a look at some affine cases, and we've got some feeling for what happens. Input an affine group, output an affine group, if you can. What about almost simple? So we thought perhaps we should try a bit harder, since we hadn't really got a good theorem yet. So we did, and we decided that we would look at the different sorts of 2 transitive groups. Remember, that's almost simple or affine, that's their name. The affine case we already looked at, the almost simple case. So if we input an almost simple case, P, then we output, we proved, an almost simple shuffle group. Okay, and eventually we could prove that if we inputted the alternating or symmetric group, in this case, K bigger than N, then we output a giant. And so that definitely was part of the conjecture for that case. So that's our K bigger than N case where we have proved the conjecture. So there's one last thing I thought I would mention. You've got this parameters. There's K and there's N. And here's the line K equals N. And if K is bigger than N, we've proved it. But this is really pathetic because we've got this whole half plane that we don't know much about. And I think we proved that if you took any K and if you had a sort of N being a power of K, we knew what was happening there. That was okay. Which just meant that you have these few dots with most of that parameter space complete mystery. So we thought we should use and explore as many different methods as we could to see what would work and what we might find out. So there's just one more thing I've got to tell you. And this is Luke's idea. Luke says, well, suppose k is a power of 2. At least 4 because Percy's done the k equals 2 case. And suppose n's not a power of 2 because we know what happens then. We've done that case. Well, the number k times n, you could factorize it. Firstly, you could factorize it the way I've got it there as 2 to the e times n, k times n. Or you might just peel off different amounts of 2 and put them in the size of the pile. And so you've got many, many different factorizations of the number of cards. And each of those factorizations, in a sense, would correspond to some shuffle group. So we decided to input the smallest transitive, just an elementary abelian regular 2 group actually on the pile of cards. So that's just our choice. And so we've got a shuffle group for every factorization, that is for every t going from 1, 2 up to e. And because we're inputting a transitive group on the piles of cards, we're outputting a transitive shuffle group. So they're all transitive groups. So we might ask, well, how are they related? And it was excruciating doing this proof of getting it first correct and secondly to be written so it was readable. But we proved one of the things, this G1, that's really special because t equals 1 means that we're looking at 2 piles of cards and we know exactly what that shuffle group is from DGK. So that one's known. So we did a lot of hard work and we proved that the G1 is kind of the biggest of them and we get this chain of subgroups. And the GE is the one we're interested in because we had chosen k to be 2 to the e. So this is the one we're really sort of interested in. Well, at least we want that value of k. Generically, we definitely get a decreasing sequence, but in fact, the index of GE in G1 is either 1 or 2 or 4. So there's not much difference between them. And so the take-home wonderful thing from this is that the GE contains most of the G1, and the G1 contains the symmetric group of number of cards over 2, or the alternating group at least. So a big sort of pile of alternating groups. But what is our aim? We would kind of like to use this bit of information to look at the shuffle group when we input the symmetric group of degree k with our n. And the symmetric group of degree k, of course, contains our C2 to the E acting regularly. And so this shuffle group contains the GE. And the GE contains a whopping biggish symmetric group. And so we could do some permutation group theory, not so difficult, and prove that in this case, our shuffle group does contain the giants, the alternating or symmetric group. So that's a completely different approach and a different class of parameters that we have found and verified the conjecture. It's terribly sparse. So I'm going to just kind of finish here. Where are we at? Essentially, we don't know. The MM conjecture is still wide open. So remember, it was more or less saying, apart from certain power cases, the shuffle group should be a giant. So we've confirmed it when k is bigger than n. I've just told you when k is a power of 2. We either get the giant or we were in a sort of power case when we also know what was happening. And we've proved it in a sort of product case. The work led to our own conjectures. First, if k is an odd prime and we're just inputting the cyclic group of prime order, and if the n is not a power of that prime k, we think that should be good enough to get the giant. No idea how to prove it, except we have pretty persuasive computational evidence that it is likely to be true. There's still more that we might look at, but we've stopped for the moment. Percy's had suggested, I think, to Kent Morrison that maybe an appropriate group, capital P, to take would be the group where the just of order 2, generated by tau, where tau is just reversing the piles. And you might think, well, that is a fairly reasonable generalization of a in shuffle in case 2. No one knows really what's going on, but Luke and I have been talking about this, and Luke's been doing some more computation, and there's something very interesting happening there, except we can't quite pin it down yet. So I think there's quite a lot to happen in the future. There's plenty of questions if someone else would like to look at it, and so I would like to end and say thank you very much. That's I hope there's someone that can do a little bit more than we can.